Now we're going to introduce a quantity here, which is called the electric field. And to introduce the electric field, so let me go ahead and let me open one of these. So let me just talk about it because this is something that is new. Now, before we talk about the electric field, let's try to understand what the so this is much more easier to understand the gravitational. So we can look at gravitational field. I think something that you can easily understand, even much more easier, is the magnetic field. So notice that the key word here is this quantity here. So let me explain to you what this means. So a field, so by definition, a field is a region where a force So a field is just a region where a force is going to act. So you can see that, for example, let's look at a magnetic field. So suppose that we have a magnet, then so we have some magnetic field lines that are going from the north to the south and things like that. So let me open again. So let's suppose that we have two magnets here. So this is north, this is south. And then I'm just going to draw some field lines. Again, this is south. So what I want you to see here is that so that region here is the range. So it means that if I were to place an object here outside that range, the magnet is not going to pull it. Does that make sense? But as you get closer and closer to the magnet, then you start experiencing the force. So the region where the force is acting is called the field, right? So what you can see in this example here, that I have two magnets. One of them has a much more larger field, right? So it means that if I were to bring something here, it gets pulled in. I put something right there, it gets pulled in by the magnet. So the force is always going to act in each of those regions right there. But once I'm outside, the force is going to be equal to 0. So 0 means that, again, it's not really 0, but we said that it's very, very small outside the range. So something that you've already seen here is that the field So I just want to introduce this because this is something that is new to you guys. So field strength is going to go as 1 over distance squared. So 1 over distance squared, if something goes as 1 over distance squared, what does that tell you about the strength of the field? It gets smaller and smaller and smaller and smaller, right? So for example, at 2 centimeters away, the force is 1 over 4 times smaller. If you double the distance, the force reduces by a factor of 4. If you triple the distance, the force reduces by a factor of 9. If you increase the distance by 5, the force decreases by a factor of 25. Now, this concept here, the field strength, again, this is what is very useful because I'll just show one example here. So now I've shown you a magnetic field. Let's look at gravity because gravity is also something that we can easily understand. And I just want to show, so suppose that so the force of gravity is always pulling objects closer to the center of the earth. This explains why if I take an object like this and I release it, as long as I maintain the same distance, the force of gravity is always going to be act, right? It doesn't matter if you're in the United States or in Australia, as long as you maintain the same distance. And the reason is because, for example, if I maintain the same distance, for example, if the height from here to here is the same as the height from here to here, the same as the height from here to here, I get the same magnitude of the force all over, right? Now, and something that is very useful here is that the Earth, so the first thing is that the Earth is a sphere, and then the force, the gravitational field, is going to go as 1 over distance squared as well. So since the gravitational field is going to go as 1 over distance squared, let me show one example here where, so this is the Earth. Let's say that, so the distance from here to here, let's call that distance R1. The distance from here to here, let's call this distance R2. So we're going to have so let me assume that R2 is twice R1. Then you see that the force at point 2 is equals to 1/4 the force at point 1. Does that make sense? That as you go outside the Earth, you're going away from the center of the Earth, the force of gravity is reducing. This explains why it's much more easier to put a satellite in a higher orbit. So when I launch a satellite very, very far away from the Earth, it's much more easier for me to launch a satellite that is very, very far away from the Earth than a satellite that is very close to the Earth. Because if I'm very close to the Earth, the force of gravity the force of gravity is too strong, right? So if I'm not careful, the force of gravity can pull in that satellite. So the only way that I can compensate that is to make sure that I give my satellite a very, very high speed, right? So for example, you guys are familiar with the International Space Station. It's an example of a very, very low Earth orbit satellite. For the ISS to stay in orbit, right, we need to launch it in such a way that the orbital speed is about 17,000 miles per hour. So that's the speed at which the ISS orbits the Earth. So at that speed, it only takes 1.5 hours to make a complete revolution about the Earth. Right. Now, if I'm very, very far away from the center of the Earth, the force of gravity is much more weaker. So I don't need a very high speed to compensate for gravity because gravity is too weak, right? But what we want to take out of this is that when we talk about the field, in this case, the Earth is the source that produces a gravitational field. And then these are the objects here. So satellite number 1 and satellite number 2, those are the objects that are being pulled, are experiencing the force of gravity. But the key point is that the strength always goes as 1 over distance squared. All right. Now, with this in mind, what we're going to do next class is that we're going to go here, and I'll just introduce this real quick. So now let's take that and relate that to an electric field. So when we look at electric field, we're going to say that suppose that we have, so this is my source. And then we say that a positive charge is always going to produce, so again, the lines of force are always pointing out. A positive charge. And then if I were to put a test charge here, Q naught, so let's say that my source is Q, and my test is Q naught. Then I can calculate the charge on my test charge as Q naught, so KE, Q naught over distance squared. And this will be pointing in the I direction, so that's the force. And then we're going to write this as Q naught times E, where E is equal to KE Q over R squared. So as from next class, instead of calculating force, we'll not calculate force, right? We'll instead calculate electric field. Then once you know electric field, you just multiply it by charge to get force. All right, so that's what we're going to pick up from this point next class, and then we'll do a few examples. All right, so I'm going to stop here and then we'll continue on.